Welcome to your first video lesson from Chapter 2. Today we are going to talk about how we represent motion. Specifically, we're going to look at uniform motion. Remember, uniform motion is motion that is constant and unchanging. Specifically, we're talking about constant velocity. Now, prior to this lesson in class, we looked at the post lab for the battery-operated car lab that we did. And we looked at how we determine velocity and certain things from a graph of position versus time. So this lesson is going to focus on being able to look at a position versus time graph and first describe the motion. The second thing that you're going to be doing now is kind of the reverse of that, is that when given a description of the motion, you are going to be able to draw or sketch a position versus time graph. Then from there, since we know some things about velocity, the next step that we're going to do then is take a position versus time graph and then graph from that a velocity versus time graph. And then being able then to next calculate velocity from a position versus time graph, which again, velocity is the slope, so that's asking you to calculate the slope. And then really kind of some of these things, this last point here is being able to understand the difference when I ask you to do something qualitative versus quantitative. What do those two terms mean in terms of graphs and some of the other things we're going to do with them? So at the end of this lesson, you should hopefully be able to do most of these things. So the first thing you're going to be doing with this method of representing motion is basically reading graphs and being able to describe the motion of an object from a graph. Now in class we discussed two of these already, and really there's going to be four things you're going to need to understand when looking at a graph. And kind of vice versa, when trying to graph something, given a motion description, you should be able to do the opposite. First we talked about the slope of the line. So what we're going to be looking at first are position x versus time graphs, so position versus time. Okay, remember that when you get a line, the slope of that line is what equals the velocity. So the slope tells you how fast your object is going. Remember, velocity is speed, velocity, kind of same thing, tells you how fast your object is moving. And with the slope, we talked about things like the steepness of the slope, how the steepness of the slope represents the magnitude or the amount of velocity you have, and also whether your slope is positive or negative. And remember, positive or negative slope represents the direction you're going. Okay. Then we talked about the y-intercept. The y-intercept is where your object starts. That's your starting position or your initial position. Okay, so if I label that as B, B represents x initial. So that is where your object is starting. So it could start at the origin, away from the origin, could start behind the origin. There's many different ways you can look at it. All right, now the last 2 points here. First, when we have an intersection point. Now this is really when we're looking at two different objects. Okay, so an intersection point, let's say if we had two lines here drawn there. Okay, you should be able to understand what this point means. What does it mean when two of these lines intersect? Okay, well, if you think about this, again, this is position versus time. So what happens at this point is at this specific time period t, both objects, both lines are at this same position. Okay, so an intersection point tells you a specific position, and specifically these two objects are at that same position. Okay, and the last thing you should be able to read from the graph is displacement. Now remember that displacement is a change in position, labeled as delta x. Now where do we see a change in position? Well, think of your graph. Where is position? Position is shown on the y-axis. So if we want to find a change in position, we're going to have to look along the y-axis. Okay, so we're going to have to look here. We're going to basically ignore time and only look on the y-axis. Okay? So we're going to look at our change in position. So take, for example, the blue line. Well, the blue line, we start here, and after a certain amount of time, I've ended my position up here. So my displacement or change in position, remember, is x final minus x initial. So if this was my x final up here, and this is my x initial down here, my displacement delta x is shown as the difference between those values. Okay, so it's this region on the y-axis. This would represent my displacement. Okay, now we're going to go through some examples and kind of refer back to some of these ideas. So first, if I were to ask you to, looking at this graph of position versus time, ask you to describe the velocity. Okay, so velocity what we want to talk about when we're describing this is we want to be able to talk about the amount or how fast it's going, and also we want to talk about direction. Okay. Now, again, where do we get these two things? Well, the amount is looking at the steepness of the slope. Okay. And direction is looking at whether the slope is positive or negative. Okay. So looking at this graph here, we can see that our slope, first of all, is positive. So what this means is that we are moving in a positive direction. And a positive direction means you are moving away from the origin. I'll put this away from 0. Okay? So you are moving away from the origin as time goes on. Now, if you want to compare your speed or the amount of velocity you have, well, look at the slope. The slope has a pretty decent steepness to it, a pretty decent slope, so that means you're moving away from the origin at a relatively high velocity. Okay? And obviously, again, the steeper the slope, the more velocity you have, the faster you're going. Now, next two things describing the starting position. Well, starting position, this is the y-intercept, or b. Looking at the graph, your y-intercept is 0, 0. So here, what I would say is I'm starting at the origin. Okay, and then the direction we've already described before, our velocity is positive. And if you look at your displacement as well, you're moving towards or to higher values of position, so you're moving in a positive direction. So how I would put all these together, to describe the motion, what I would say is that this object starts at the origin and moves away from the origin, so that's talking about direction, moves away from the origin at a constant positive velocity. Okay? Now, it's tough right now because we don't have numbers, so we can't describe any values to it, but what I would say, again, it starts at the origin and moves in a positive direction with some constant velocity. And now all of the examples we're going to do is going to be applying these certain things. Okay, so here's a graph of two different objects, A and B. Now, looking at these, we want to be able to describe kind of the same things we did just in the last example, was looking at velocity, direction, initial position, and all those sorts of things. Okay, but now we're comparing two objects. So first question here, who is moving faster? Okay, so who is moving faster? Well, how do we determine how fast they're moving? Well, again, this is the steepness of the slope. So looking at object A compared to object B, we can see, and it's pretty obvious, that object A has a steeper slope. So here, object A would definitely be moving faster. All right, do they start at the same point? Second question, how do you know? Well, starting point is represented by the y-intercept. So here we're looking at the y-intercept. Okay, so we want to know, do these objects have the same y-intercept? Well, object B has a y-intercept there, and A has a y-intercept there. So no, they do not start at the same point. They do not. Okay, object B starts away from the origin, and object A starts at the origin. All right, next question. This is kind of a tricky one. Are the velocities equal at any time? Okay. Now, one common thing to look at, or one kind of mistake here, is, okay, you can see that the two lines intersect. Now, what does that intersection point mean? Okay. Does it mean their velocities are equal, or does it mean, the next question, are their positions equal? Okay. Well, let's think about, well, where do we find, for example, the first one, where do we find velocities? Well, velocity, remember, is the slope of the line. So this question is asking you, do these two lines have the same slope? Okay? If they had the same velocity, they would have the same time or the same slope, right? Well, ask yourself this, what do two lines look like that have the same slope? Think mathematics. Well, two lines with the same slope are called parallel lines. Okay? So looking at objects A and B, are they parallel lines? Do they have parallel or equal slopes? In this case, no. So the velocity is not the same at any time. They are never the same. Now, the velocities for A and B are constant. They're the same for each one, but they are not the same. They're not equal to each other. So velocity A does not equal velocity B. So what does this intersection point mean? Well, remember that this is a position versus time graph. So at 5 seconds, this intersection point is telling me that at 5 seconds, these two objects are at the same point. Okay, so they're at the same point. What that means, if I were to draw a picture, say this is my origin, here was object A, here's object B that started away from the object, here's object A. That means that as object B moved along, object A was moving faster, and at some point they are at the same location from the origin. So this location right here, I'll call it delta x, is the same for both A and B. So an intersection point tells you position. In this case, XA, position of object A, would be equal to the position of object B. So at this time of 5 seconds, they'd be at the same position, not necessarily the same velocity. Okay, so the last examples looked at, given a graph, we want to describe the motion or compare two objects. Now we're going to do the opposite. So now we're going to take a description and we are then going to sketch a graph. So we're going to do the opposite now. Now, right now we're looking at just a sketch, so there are no values. Okay, so this is one of the things I wanted you to get out of this lesson was knowing the difference between quantitative and qualitative graphs and things like that. Okay, if you think quantity versus quality, just want to go over this quickly. When I say quantity versus quality, what's the difference? Well, quantity talks about an amount. So this one, if we have an amount, we have numbers. Quality is kind of describing the object, so this is just a description. Okay? So when I talk about these two things, quantity, when I talk about a quantitative graph or something that's quantitative, it's going to include values. Okay? When I talk about qualitative, it's going to be a pure description or just a basic sketch that just shows the general relationships. Okay? So those are the difference between the two. Now, let's focus on what we did before. We took a graph and we tried to describe the motion. Now we're going to do the opposite. So again, when we're looking at a description, trying to graph it, there's a few things we want to talk about. First, we want to know where is it starting. So what's the starting position? Which direction is it moving? So does it have a constant positive or negative velocity, or is it moving towards or away from the origin? And then, is it speed? Like I said, obviously right now it's going to be constant. Okay, so is it constant? Yes, it is. And then is that velocity positive or negative? Okay, and then if we're given numbers, what's the general what's the general value of the velocity? Is it large or small, so I can sketch the steepness of the slope accordingly? Okay, so let's look at this example. An object moves away from the origin at constant speed. Okay, well, thinking about this, right, if it's moving away from the origin, it has to start. Think of starting point. It's just going to start at or near the origin. I'm going to assume right now it's starting at the origin. So the origin is 0, 0. So my first point I would draw at the origin. And now it's moving away. Okay? So as time increases, your object is going to move away from the origin. So if I were to sketch the line, I would start at the origin and move away. And to show that I have constant velocity, I need to make sure that this is a straight line. Okay? Because remember that a straight line has a constant slope. And that means that this is going to have a constant velocity. So the graph of an object moving away from the origin at constant velocity would be drawn like this. Okay? Again, we're showing starting position. We are showing that it's constant. We are showing that it's moving away from the origin, right? And that the velocity obviously is constant. Okay, this next example now is a multi-part problem. So this one has two parts. Okay? Now what I want you to do for a two-part or multi-part problem, right, is to break it into each individual parts. So in this problem, we have an object moves away from the origin at constant velocity for 5 seconds and then stands still for 10 seconds. Okay? So notice how you have constant velocity and then stand still. Okay? So we have two different types of motions all in one situation. So what I want you to do in this type of problem is I want you to break this in half. I want you to draw first the first 5 seconds. So I'm just going to put some marks on here. Okay, I'm going to assume, let's say this is by 2s, 2, 4, 6, 8, 10. Okay, so for the first 5 seconds, that means from 0 to 5 seconds, which is there, I am moving at a constant velocity. Now it says here too, an object moves away from the origin. So remember, let's think again. Let's just analyze the first part. So the object moves away from the origin at constant velocity. Well, that's the problem we just looked at. I'm going to assume it starts at the origin, and if it's moving away from the origin, it's gaining position as time goes on. So from 0 to 5 seconds, it's moving at a constant velocity away from the origin. Okay, so there's my first part. I'm going to continue this dashed line. Now let's look at the second part. It says, and then the object stands still for 10 seconds. Okay, so for 10 seconds, I'm at 5. I need to go all the way to 15. So here's 12, 14, 16. Okay, so I'm going to be going all the way up to 15 seconds. Okay, now let's think about it. What does it mean to stand still? Well, to stand still, standing still is still constant velocity, but your velocity is at 0. All right, now think about this. Standing still, your velocity is equal to 0. Well, where do you get your velocity on a position versus time graph? Velocity is equal to the slope. Okay, so that means your slope must equal 0. Well, how do you show a line with 0 slope? Well, a line with 0 slope is simply a horizontal line. Okay, so how you represent something standing still is by a horizontal line. This is showing that after 5 seconds, you were at this specific position, right here, whatever this is, and you stayed at that spot for the next 10 seconds. Okay, so when you're given a multi-part problem, you want to break it in half and analyze each one separately. Okay. So up to this point, you should be able to both understand a graph in terms of its motion, and also to be able to sketch just a basic position versus time graph given a description of the motion. Now we're going to take it a step further, and we're going to go on to the next type of graph, which is a velocity versus time graph. So instead of graphing position in meters, we are going to look at an object's velocity in meters per second. All right, now the key thing to think of is right now we are dealing only with uniform motion, and uniform motion means that your velocity is constant or unchanging. Okay, so to answer this first question, what does it mean to be constant? Well, it means that it's unchanging. Okay, so your velocity is unaffected. It's the same throughout. So if you think, what we're going to try and represent is a velocity versus time graph. So what you have to think about is mathematically, how would you graph something that's unchanging, something that is constant? So what we're going to look at is, if velocity is unchanging, that means as time is going up, as time is increasing, so as time is increasing, what happens is that your velocity is staying the same value. Okay, so right now let's just assume that we have maybe we're moving at some positive velocity. So if you think of like a position versus time graph, let's say that we start at the origin and move away at a constant speed. What we said is that this motion represents that, again, we're moving away from the origin, we're moving at a constant speed because it has a constant slope, all right, and that our direction is positive because we're moving away from the origin. All right, so representing that on the velocity versus time graph, what we're going to do is we're going to show that the velocity is constant or unchanging, which is simply a horizontal line. Because what this is telling you is that as time goes on, you are maintaining this same velocity, that your velocity is not changing. So if I were to look at different time values, my velocity is exactly the same. Now, what a velocity versus time graph does not allow you to do is to talk about your initial position, or x initial. Okay? Why? Because if you think of a velocity versus time graph, it does not show you position. It is only showing you velocity with respect to time. So you have no idea what position is. So one of the main things you might want to do with these velocity versus time graphs is to try and sketch a position versus time graph first. And by that sketch of position versus time, that'll kind of help you to understand what's going on in the velocity versus time graph. Okay, so let's do an example. So this is one we did before. What we're going to do is, given this description of motion, I'm going to sketch a graph. And from the sketch of position versus time, I'm going to also sketch a velocity versus time graph. So here is the description. It says an object is moving away from the origin at constant velocity. Okay, so what I'm going to assume in this problem, just to kind of change things up, is I'm going to assume that it does not start at the origin. I'm going to say it starts at some initial position that we don't know. Again, this is just without numbers. Okay, so we don't have any numbers, but we're just talking in general. So it's starting with some initial position, and it's moving away from the origin. To show it's moving away, I'm going to gain position as time goes on, and I'm moving at constant speed, so I need to make sure I have a direct relationship. So to move away as time goes on would look something like that. Okay, so there's kind of a quick sketch of my position versus time. Now let's take this and let's correlate it now to the velocity versus time. So again, what we're looking at is constant velocity motion, meaning, again, constant means it's unchanging or it's the same throughout. So thinking about where we get velocity, looking at position versus time, recall that the velocity is equal to the slope. Okay, so the slope represents our velocity. Well, the slope of a straight line or a direct relationship, in mathematics, the slope never changes. Okay, to be a direct relationship, that means that no matter where you look along this line, if you choose any 2 points, you should get the same slope. So the slope is constant. That's where we're getting this constant velocity from. So how we're going to show this on velocity versus time graph is that we have, from the start, some initial velocity. Now the key thing here with velocity versus time, as opposed to position versus time, is that this point right here no longer represents our initial position, but this represents our initial velocity. Okay? This is kind of a key difference. This represents initial position, that's initial velocity. And since we are not changing speed, we're moving at a constant velocity, as time goes on, since my slope is constant and positive, my velocity is going to be unchanging and positive. Okay? So notice how we are going from here a direct relationship to really what's a no relationship graph, or something that's unchanging. Okay? There's no effect. Okay, for any students that may be in calculus, this brings up kind of a quick point. And if you're not in calculus, you can kind of fast forward and ignore this next point. If you think of a graph, in this case you have a y equals x graph. Okay, the slope here represents the velocity. The velocity we defined as the rate of change of displacement. Those of you in calculus may know this to be the time-based derivative of position, or displacement in this case. Okay. Well, if your curve is of the form y equals x, if you were to take the derivative of that, you would get y equals a constant. Okay? Because you get rid of the x, you drop the x, and all you would have is a constant. So this is kind of how that graph comes to be. Is really, this physics is all just kind of an application of calculus. All right, let's do one last example here. This example is now a multi-part problem. We did this example with position and time, and now we're going to take this and apply it to the velocity versus time graph. So what we have is an object move away from the origin at a constant velocity for 5 seconds, and then stand still for 10 seconds. Okay. So on this graph, I'm not going to draw the time intervals, but I'm just going to quickly sketch it. Let's say that this right here represents 5 seconds. Okay. So it says the object moves away from the origin at constant velocity for 5 seconds. In this case, since I'm not told what x initial is, I'm going to assume it's 0. I'm going to assume, because I'm moving away from the origin, that I start at the origin. Right? It should make sense. If you start at the origin and you walk away from it, you're going to move, obviously, away from it in a case of positive direction. So what happens is here I move away at a constant velocity. So constant velocity, again, I have to show with a straight line. So I'm moving away from the origin, constant velocity, until I reach this time period of 5 seconds. After 5 seconds, it says the object stands still. Okay? And it stands still for 10 seconds. Alright, so how do we represent standing still? Well, standing still means you are not, once you get to this position that's right here, you are not changing your position. You are staying right there. So, as time moves on, your position does not change. So if I count out 5 or 10 to 15, okay, this is what the graph will look like of position versus time. Now here's the tricky part. Now we got to correlate this to the velocity versus time graph. Okay? The one key thing about position versus time, velocity versus time, there's one variable that's not affected as we go from position to velocity, and that's time. Okay? Time is always the independent variable. It's something, I guess, we can use, but we can't really control. All right? So the time intervals that we have for position, 5, 10, and 15, are going to be the same on velocity, because time cannot be different because we're talking about the same motion in the same object. So I'm still going to have the same time periods. So I'm going to split this up just like I did into 2 sections. Okay? So this motion is part 1, and this is part 2. And again, to analyze motion, and I didn't really talk about with position, but you want to analyze each separate motion separately. Okay? So the first one, an object moves away from the origin at constant velocity. Now looking at my position versus time graph, my velocity again is represented by the slope, okay, and my slope is constant and positive. So how would I represent that is I initially start at some velocity, so this is my v initial, and my velocity is constant, meaning it's a horizontal line, and notice my horizontal line is in the positive region, so it's a positive velocity. Now once I get to 5 seconds, the object then stands still. Well, if you think of velocity, what does it mean to stand still? Stand still, your position is not changing. Velocity is defined as a change in position over time. So if delta x equals 0, then your velocity is going to equal 0. All right? Now, where is 0 velocity on this graph? Well, if you think of the axes, x and y, when you have your x-axis is always located where y is equal to 0. So along this line is where you have your 0 velocity. So how I would represent this portion of the graph is from then 5 to 15 seconds, I'm at 0 velocity. So I'm along that line because this right here represents v equals 0. All right, now here's one last little point here. Notice here that I skipped the region between my positive velocity and 0. So what do we put there? Well, the way I want you to label this is with a diagonal line that connects the two lines. Why diagonal? Is because if you're going from this velocity to 0 velocity, you must be in between. It's impossible not to be in between. And you cannot go from this velocity to 0 velocity without any time going by. So there has to be some time that goes by. So the slight diagonal line is showing that you are changing speed from whatever to 0, and it's also taking some time to do that, which must be true. So this is an example of going through position versus time graphs and velocity versus time graphs for a multiple object.